Okay, here we go. This is AP Classroom, Unit 6, Free Response Question Set B, Question 1, and a graphing calculator is required for this question, so you are not able to do this without your calculator. You have to use your calculator to work through this. Background information, and this problem actually starts right here. Let f be the function defined by f of x is the cosine of square root of x. You want to approximate the definite integral using a midpoint Riemann sum with these are the subintervals. Show the work that leads to your answer. So moving to another piece of paper here. Part A, we want to find the integral from 1 to 3 of f of x dx by using a midpoint Riemann sum. Now you can't use the Riemann sum or num_int or num_int2 on your calculator because those have evenly spaced intervals. These guys are not. This length is 0.6, this length is 0.4, and this length is 1. Sometimes to help get a visual of what we're doing here, I'm just going to make a quick graph. I could look up what cosine of square root of x looks like on my calculator, but it really doesn't matter for what I'm doing right here. These intervals go from 1 to 1.6, from 1.6 to 2, and from 2 to 3. And I want midpoint heights. So the first interval right here, take that up to where it hits the function. There's your first rectangle with midpoints. Second rectangle, find the middle. Take it to where it hits the function. There's the second rectangle. Third one, right there. So we have 3 rectangles here. The first rectangle is the width, so 0.6 times the height. And the height of that rectangle is going to be where the midpoint hits that curve. So that hits the curve there at, the middle is at 1.3. So that's going to be f of 1.3. Plus, second rectangle is going to be the middle between 1.6 and 2. That's 1.8. But how wide is this? It is 0.4 wide. 0.4 wide, and then the height is going to be where 1.8 is plugged in, plus, and then the third rectangle, it is 1 wide times what gets plugged in, 2.5, f of 2.5. Okay, now to do this on your calculator, I actually have this function typed in at y3, but if you put it in at y1, that's perfectly fine, but your calculator will do function notation. So to do this, go back here, and we want to do 0.6, and then I want to do the function at 1.3. Well, my function is in y3, so I'm going to go here. So I did alpha f4, y3 is number 3. If yours is in y1, use y1 of 1.3. And then I want plus 0.4 times f of 1.8. So mine is y3 of 1.8 plus, and then my last one, I want 1. You don't have to write the 1 times y3 of 2.5. And that gets 0.3309. So all of this is 0.3309. Okay, point values on this one. They gave you +1, different color here, for midpoint sum. And then they give you +1 for the answer. All right? Part B says, approximate that integral using a trapezoid sum with those intervals. Show the work that leads to your answer. Oops, sorry, I had it on the screen. All right, so we're doing the same thing, kind of, only this time we're not doing midpoint sum, we're doing trapezoid sum. And you cannot use the straight up trapezoid rule because the intervals are not evenly spaced. So you're going to have to do a trapezoid individually here. That was 2.5, the last one. All right, so for part B then, you want the integral from 1 to 3 of f of x dx is approximately, and we're going to use trapezoids. So you have to remember the formula for area of a trapezoid, 1/2 height times base 1 plus base 2. And in these trapezoids, they're stacked sideways. So the height is actually this distance in here, and the base 1 is this one, and base 2 would be this one. The two verticals are the bases there. All right, so for this first trapezoid, the one in pink, that one's going to be 1/2 height. Okay, the height is the distance in here, so 1/2 of 0.6 times, and then the two bases, so this is going to be f of 1 plus f of 1.6. There's the first trapezoid. Second trapezoid, 1/2 height, its height is 0.4, and then its bases, f of 1.6 plus f of 2. And then our third trapezoid, 1/2 height, so 1/2 times 1 times its bases, f of 2 plus f of 3. Oh my. So in your calculator, here we go. Yikes, this is an exercise in button pushing actually at this point. So I'm going to do some of this in my head. Half of 0.6 is 0.3. So I'm going to 0.3 times, now I need f of 1. Remember that function was in my y3. It might be in your y2. y3 of 1 plus y3 of 1.6, and then close off the parentheses there for those outside ones. Okay, now I'm going to do these three individually. So here, enter. That's that first one. Now, this is kind of a trick. I just have to change a few things here. So I'm going to go second, enter, which repeats that previous line. And then I can go back in it and just change out some of these numbers. So half times 0.4 is 0.2. And then I want y3 at 1.6. So I'm going to go here and I'm going to insert. So second insert, or second delete, gives me 0.6, 1.6. And then I need this at 2. Delete, delete, f of 2, enter. So there's my second one. And now my third one, I'm just going to repeat that line again, and now I can change. Half of 1 is going to be 0.5, and I want f of 2, so y3 of 2. I'm going to delete this out, the 0.6 out, and then y3 of 3. So there's my 3. Now, to add those 3 up, I can go back, and I can just arrow back up. Oops. Arrow back up. Grab either the answer or this line, this one, plus arrow back up, and I want the 1.6 and the 2 one, this one, and then plus the 2 and the 3 one, this one. So I'm just going to check them and then enter, and I get 0.3415. As I said, exercise in button pushing on your calculator. You do not have to do it the way that I did. However you do this, that's fine. Just if you choose to write down the numbers, don't round off in the middle of the problem. That's a big deal. You'll get a wrong answer there if you round off in the middle of the problem. You have to carry all those decimals with you, which is why I like to do it this way. So this was 0.3415. So they would accept 0.341 or 0.3412. I'm going to go back up here. This one, they would accept 0.330 or 0.331, rounded or truncated, either way. All right, point values on this one. You do get 1 point for the trapezoid approximation. Just kind of setting it up, and then +1 for the answer. Okay, all right, part C now. Part C, it is known that F prime is that mess and F double prime is that mess. Would a trapezoid sum approximation for this overestimate or underestimate the value of that function? Give a reason for your answer. Okay, so for this one, it's going to depend on the shape of your curve here, if that trapezoid is above the curve or if that trapezoid is actually underneath the curve. So it depends on the shape of the curve. So what I'm going to do is I'm going to take a look at f prime of x, and I'm going to look at f double prime of x in terms of if they are positive or if they are negative on that particular interval from 1 to 3. And if these guys are, if f prime is positive, we know that f is increasing. F prime negative, we know that f is decreasing. F double prime will tell us whether f is concave up or concave down. So I'm going to go take a look at both of those and see what that tells me about the shape of f. Now, on my calculator, this is why I had f in y3, because I had already put in f prime in y1 and f double prime in y2. Okay, I am interested in these on the interval between 1 and 3. So my window, I went a little bit bigger. I went from -1 to 4. And I'm only interested if these guys are positive or negative. So I made my y's pretty small here, just between -1 and 1. When you graph these, I'm going to go back and check color again. So my y1, f prime is blue, and my y2, f double prime is red. And here's the graph. So f prime was blue. So on this interval from 1 up to 2, 3, this interval right here, from 1 to 3, f prime is blue, so it is always less than 0. F prime is less than 0 for this interval. And f double prime, which was red, it is above the x-axis, so it is always positive on this interval. So that means f of x is decreasing, and f of x is concave up. All right, that means that my f of x graph, decreasing concave up, and if I draw in one really wide trapezoid here, that trapezoid is above the function, so it overestimates the actual value. of the integral. Okay? All right, so point values here. You're getting +1 for considering the f double prime. Actually, concavity is the only thing that affects whether a trapezoid sum is an overestimate or an underestimate. So it didn't matter that we checked f prime, but I think it's complete to think about it that way. So I did both here. And then the +1 is for overestimate with reason. So you have to say why. Which your reason actually is right up there. So you considered f double prime. Now, if you got f double prime, you considered it, but for whatever reason you said it was less than 0, you won't get this point. You'll get this point because you considered f double prime, but you won't get that point. Okay? All right, part D. Now, part D, I think, is the toughest thing for this particular problem because they want you to relate an integral to a right Riemann sum. So, oh boy, be patient with me because there's a lot of kind of theoretical and general stuff going on in here to try and get you to see how this works. So, I need you to go back to when we first learned about Riemann sums. We said that an integral from some spot a to b of f of x dx was the limit as n goes to infinity of a sum from I equals 1 to n of some f of c sub I times delta x. Oh boy. So this is summing an infinite number of rectangles. These are your counters. I equals 1, first rectangle, second rectangle, third rectangle, etc., going up to an infinite number of them. So we're summing where these guys here are your heights, and this is the width. Remember something like that? All right, now the widths is delta x is always the length of the interval, so b minus a divided by the number of rectangles. So what this problem is asking you to do is to take this integral from 1 to 3 of f of x dx and write it like this, so it looks like a limit. So we're going to fill in the parts that we know. So we have the limit as n goes to infinity, a sum from I equals 1 to n. Now we know it's going to be f of something. We're going to have to figure that out, times the delta x. Well, our delta x, we know, is b minus a, so 3 minus 1 over the number of rectangles, infinite, but we're just going to leave it like that, so 2 over n. So we can plug, that's not an h, that's an n, so we can plug that right in here, so that's 2 over n. Okay, now the tough part, trying to figure out what's going to go in here. Because they want this to be a right Riemann sum, I'm going to come back down here and get a picture of this function going up here to kind of explain to you what's going to go inside of here. So it started at 1 and it went up to 3. Okay, first rectangle, second rectangle, down here, nth rectangle way down there. So this spot, if you're doing a right Riemann sum, then for this first rectangle, I need to start this at this point right there for that right Riemann sum. And this one needs to go there for that right Riemann sum. So the first value that goes in here actually is going to be this spot right there, which is 1 plus delta x. Oh, golly, it froze. Ugh. Oh, so close to the end, too.